Okay, good morning, everyone. I hope you can hear me clearly and can see the screen also clearly.
Good morning, sir. All clear, sir.
Good morning, sir.
Good morning. Thank you both very much. Okay, so a very quick recap on what we did yesterday, the transformer losses. What are I squared R losses? The I squared R losses are also called as copper losses. Okay, we presume that copper is a very good conductor of electricity. Okay, but silver is even a much better conductor than electricity. Just like when we talked about ICCP, we said seawater is a much better conductor than fresh water. Why? Is because the number of free electrons, which are the carriers of current, will be much more in one than compared to the other. Okay, so that means if you're going to say silver is a better conductor than copper, that means copper is going to offer more resistance to the flow of electricity as compared to silver. So that resistance, you're going to have current flowing. And when current is going to be flowing through a resistor, a voltage drop will be across the resistor, and that is going to heat the resistor. Okay, and here in this case, the resistor is nothing but the conductor itself. Okay, so this particular loss is called a copper loss because it is in the form of heat that is wasted. It's not doing any good work. It is just wasted energy. And because it is also due to the current, I squared R, more the current, more would be the loss. Okay, so you cannot help this excepting increasing the cross-sectional area, because we know rho is equal to, let me write that down. Okay, rho is not equal to, directly proportional to length over cross-sectional area. So you have to increase the cross-sectional area so that this resistivity comes down. But then we are limited to the cross-sectional area. We cannot have a very large cross-sectional area. And then when you're going to have that cross-sectional area, things such as skin current, etc. come on. Just give me a moment, please. Okay, sorry for that. This thing, they wanted me to shift my car. They are doing some work. Anyway, I've told my wife, so she'll do that. Yeah, okay. So that is what is I squared R losses or copper losses. You can only reduce your copper losses, I squared R losses, by increasing your cross-sectional area, but then you're going to be limited by that. Okay. If you're going to have large cross-sectional area, as I said, you can have skin effect because we are dealing with AC over here. Okay, and also the size of that particular motor or transformer, that's going to become much larger. Okay, so size and all that has to be taken into consideration. So somewhere in between, one has to compromise over there. Okay, you cannot get rid of I squared or copper, I squared R losses or copper losses completely. Not possible. Then we saw two losses. They are both iron losses, eddy current loss and hysteresis loss. Why is it called iron core losses or iron losses? Why? Is because we are using a soft iron core in order to concentrate the electromagnetic lines of force from your primary to link your secondary at its maximum. Okay, so because we are using this soft iron core, we are going to be having eddy current loss and hysteresis loss. Eddy current loss is because being a soft iron core, your primary is going to induce a voltage. We saw yesterday that video. it's going to induce a voltage into that soft iron core. And when voltage is induced in that, you have currents that are going to be flowing. And that current is called as the eddy currents. Okay. And eddy currents are going to be such that it is going to counter the original electromagnetic lines of force. Why? Because eddy currents are going to be having their own electromagnetic field. And that electromagnetic field is going to counter your primary electromagnetic field. And if that is going to happen, then the amount of electromagnetic field that is going to link your secondary will be diminished, which means you're not going to get sufficient amount or the exact amount of voltage induced into your secondary. So that is a loss. How do we reduce these losses? We saw instead of having a solid soft iron core, that solid soft iron core, be it the shell type or be it the hollow type, they are cut into very, very thin slices. And each of those slices are insulated from one another and then brought together to form a block. So you're not going to have these eddy currents flowing that much. It's going to be drastically reduced. If it was 100% earlier without those slices and insulation, then it is going to be now reduced to at least by 90 to 95%. But still there will be some eddy current losses which are not or cannot be eliminated totally. Unless you're going to have a certain particular thing, and that is core, which will reduce that even further, and that is why they are going to be using nowadays cold rolled steel. Cold rolled steel, which will reduce these eddy current losses even further. But still, again, you're going to cut it into very thin slices and insulate each of the slices from one another. Then we did yesterday, we made a start on the hysteresis loss. Again, this hysteresis loss is because of that soft iron core. It's a thing that is going to get magnetized. Okay, so let's say, okay, this is that, 1 second, let me get back to this. Just give me a moment. Yeah. Okay. So if this is a piece of metal and you're going to force a current to be flowing through it, this current that is flowing is going to be called as the magnetizing current. Inside this piece of metal, you're going to have a lot of tiny, tiny magnets. Okay. North, south, south, north, all mixed up. Okay. Okay. So in other words, this soft iron core is not magnetized. In other words, it is all hera-fairy. Okay, like this, all mixed up. And because this magnetizing current is going to be flowing, depending on the direction of flow of current, remember we are talking about AC. So, and one time the current is flowing in this direction, another time the current will be flowing in this direction. Okay. So let's say when the current is flowing in this direction, all these particular magnets which are scattered around at random will become organized in this manner, all north pointing in one direction, all south pointing in another direction. Okay, so if you're going to plot a graph of the magnetizing current and the flux density, remember the flux density is going to be with regard to this magnetizing lines of force. Okay, so as your current is increasing, these particular magnets will start arranging themselves, for example, in this manner. Case 1. Okay. And then you're going to reach your peak of the thing, by which time all the particular magnets will become like that. In other words, you're going to get saturation. If you're going to increase the current further, that's not going to change anything because all these tiny magnets have become arranged here as in case 1. Okay. Now, case 2. This current is becoming less and less now towards 180. And therefore, when it's going to become less and less, once again, these magnets are going to try and come back into the original mixed up position. But from this, not all of them are going to change once your current has reached 0. You would expect it that once the current has reached 0, it will be back into this original. So let me mark this as original. Okay. As in this case, it is not going to be like this, all mixed up. So then what happens? Okay. You are going to trace a path in the opposite direction. When I say opposite direction, you have to change your magnetizing current in the opposite direction. Up till here, you're still having some, as you can see in this case here, this was all arranged in north and south. Some of them are still remained in the north-south direction. Some have already changed with the south-north direction. And some have become on the way to changing into the south-north direction. So you are going to retain some amount of magnetism, which is going to be in this direction. And that, if you remember what I said yesterday, that is what we call as residual magnetism. You are retaining the magnetism in this particular direction, not a full magnetism, but partial magnetism. And that is what is called as residual magnetism. That is what we are talking about when we are going to be starting our generators. There's going to be residual magnetism in the exciter coil. And based on that residual magnetism, you are going to be able to develop your voltage for your generators. Okay. So then, in order to bring it back into the original position like this, you have to take that magnetizing current and take it in the opposite direction. That means now from positive side, you've gone to 0, and now you're gone into the negative side of your AC cycle. And that is depicted here on this particular graph in the negative direction. This is the positive direction. This is the negative half of your AC cycle. And when it reaches this point over here, okay, let me change that color. Make it black rather. Okay. When you reach that particular point over here, it is at that point when it comes into the original position, all mixed up. Okay, it is no longer magnetized. But from here to here, you have consumed electricity, you have consumed power in order to bring it back into the hera-fairy or mixed up position, the original position. That is this energy. The area covered by this curve as shown in red is called the area of retentativity. That is up till here. Okay. That is called as the area of retentativity. Now, this is that extra current that is required. So that means you're wasting energy to bring this back into this original position instead of coming back to the original position at this point. So this much extra energy is consumed and that energy is wasted. Okay. So now we have gone into the negative territory. And once again, as the current is increasing in the negative direction, once again now from this position, okay, it's come into this original position. From here, it is going to come to this one. Okay, so that is why I've drawn these arrows like that. From here to here, back to the original position, and now you've gone back into where the polarity has been changed. Here it was north-south, now it has become south-north. And that is the pace where you're going to be reaching, where the maximum magnetizing current. All the magnets are now changed in the opposite direction. Therefore, you're going to get saturation once again in this thing. And then again, this particular cycle is now becoming more and more, proceeding towards the positive half, is becoming less and less the magnetizing current. So just like as here it was coming in this direction, here also it is not going to come to zero. You're going to have this type of situation somewhere in between. And therefore, you'll come up to this particular point, okay? This particular point where there will be again some residual magnetism. Some of these magnets will still remain with the south-north direction. Some would have changed to the north-south direction. Some of them would be in between somewhere. You'll come like this. Okay, you'll come into this particular position. Okay, and then finally at this particular point, you'll come back to the original position. So if you're going to trace and have this particular curve, this is called as the BH curve or the hysteresis curve. So if this curve is going to be fat, okay, really fat, okay, then the energy that is going to be lost is determined by the fatness of this curve. If you are going to have a curve very slim in nature, okay, it's not very accurate, but you can get the idea what I'm talking about. If it's going to be very slim in nature, that means this energy that is consumed here by for changing around it back into the original position, that is minimized quite a bit. So that energy is going to be saved and you're going to reduce your hysteresis loss in that manner. Again, how do you reduce your hysteresis loss? By having cold rolled steel rather than soft iron core. Okay? You will never get something where you will not have this curve. Ideal would be a complete straight line, isn't it? Where no energy is lost. As you're coming down to zero over here, everything is changing to this. And as you're coming down to zero over here, everything is changing. So ideally, you would like a nice straight line like this. But as I said, on this earth and in this world, nothing is perfect. You don't have such a material. All that you can do is use that cold rolled steel, which will make this particular thick fat BH curve or hysteresis curve a little bit slimmer, okay? But you will have hysteresis loss. Okay? Is everybody clear with regard to hysteresis loss? And why is it so?
Excuse me, sir.
Hmm.
So this red and blue area is equal?
You can say so. Almost. It's not exactly equal. It will be more or less equal. Okay? There'll be slight difference between each. But that's not the point. It's only with regard to the amount of energy that is consumed in order to bring it back to the original non-magnetized position.
Okay, sir, got it.
Okay, so if you have understood what I've just now explained, let us see a video. It is in Hindi, those who understand Hindi, and I think most of us understand Hindi, you will now realize what exactly is happening. Okay, so let's have a look at this.
इस लॉस क्या होता है? हम यह तो जानते हैं जब चार्ज मोशन में होता है तब मैग्नेटिक फील्ड बनाता है। न्यूक्लियस की परिक्रमा करता हुआ इलेक्ट्रॉन इस प्रकार मैग्नेटिक फील्ड बनाता है कि एक तरफ मैग्नेटिक लाइंस का उत्सर्जन होता है यानी नॉर्थ पोल बनता है और दूसरी तरफ मैग्नेटिक लाइन फोर्स का आगमन होता है यानी साउथ पोल बनता है। इस प्रकार एटम अपने आप में एक मैग्नेटिक डायपोल होता है।
एटम्स का झुंड मिलकर डोमेन्स बनाते हैं। जरूरी तो नहीं कि डोमेन्स में हर एटम का मैग्नेटिक अलाइनमेंट सेम हो। कुल मिलाकर डोमेन की बाहरी परिधि पर कुछ न कुछ रिजल्टेंट मैग्नेटिज्म मिलता है, यानी डोमेन भी अपने आप में एक मैग्नेटिक डायपोल होता है।
कुल मिलाकर कोई भी फेरोमैग्नेटिक मटेरियल जैसे लोहा, सिलिकॉन, स्टील आदि को मैग्नेटिक फील्ड में रखा जाता है तो मटेरियल में उपस्थित यह डायपोल मैग्नेटिक फील्ड के अनुसार अलाइन होने लगते हैं। एक्सटर्नल फील्ड के नॉर्थ पोल की तरफ डायपोल का साउथ पोल अट्रैक्ट होता है और साउथ पोल की तरफ नॉर्थ। इस प्रकार एक्सटर्नल मैग्नेटिक फील्ड को एक आधार मिलता है, सपोर्ट मिलता है कि वह मटेरियल में से पास हो सके मजबूती के साथ। इसी कारण से फेरोमैग्नेटिक मटेरियल की परमिएबिलिटी यानी परागम्यता अधिक होती है और मैग्नेटिक फील्ड दूसरे माध्यम जैसे एयर की वजह फेरोमैग्नेटिक मटेरियल से गुजरना पसंद करती है। यही कारण है कि बहुत सारे इलेक्ट्रिकल मशीन्स जैसे मोटर, ट्रांसफार्मर आदि में कोर के रूप में फेरोमैग्नेटिक मटेरियल का उपयोग करा जाता है। मैग्नेटिक फील्ड को हटाने पर डायपोल्स फिर से इधर उधर हो जाते हैं और मटेरियल के अंदर उत्पन्न हुआ मैग्नेटिज्म समाप्त हो जाता है। जैसे कि एक इलेक्ट्रिकल ट्रांसफार्मर में मैग्नेटिक फील्ड अल्टरनेटिंग नेचर की होती है, जिससे कोर के अंदर डायपोल अलाइनमेंट चलता रहता है। अलाइनमेंट के दौरान डायपोल्स की बाउंड्री आपस में रगड़ती है, फ्रिक्शन उत्पन्न होता है और हीट उत्पन्न होती है जो किसी काम की नहीं होती। इसे ही हिस्टैरिसीस लॉस कहते हैं।
हिस्टैरिसीस लॉस को हम बीएच कर्व के हेल्प से भी समझ सकते हैं। जैसे कि हमारे पास एक फेरोमैग्नेटिक मटेरियल है।
Okay, so this is that soft iron core. You can see it is all mixed up. There is no particular direction where there is north and south. Okay, so it will be non-magnetized.
जैसे ट्रांसफार्मर की कोर में यूज करते हैं सिलिकॉन स्टील, इसमें का अलाइनमेंट इधर उधर होता है और इन डायपोल्स का अलाइनमेंट ऐसा होता है कि ये एक दूसरे के मैग्नेटिज्म को कैंसिल आउट कर देते हैं। अब हम एक कर्व ड्रॉ करते हैं जिसे बीएच कर्व कहते हैं। यह ड्रॉ होता है एच, यहाँ पर एच एक्सटर्नल मैग्नेटिक फील्ड इंटेंसिटी है और बी के बीच में। यहाँ पर बी क्या है? बी है मैग्नेटिक फ्लक्स डेंसिटी इनसाइड दी मटेरियल। तो शुरुआत में जब कोई भी फील्ड, आप यहाँ देख सकते हैं कोई भी फील्ड नहीं है, कोई भी एक्सटर्नल फील्ड अप्लाई नहीं करी गई है, मटेरियल के अंदर मैग्नेटिक फ्लक्स डेंसिटी भी जीरो होगी क्योंकि सारे डायपोल्स इधर उधर अलाइंड हैं और एक दूसरे के मैग्नेटिज्म को कैंसिल कर देंगे। फिर जब हम इस मटेरियल को किसी एक्सटर्नल मैग्नेटिक फील्ड में रखते हैं तब क्या होगा? आप देख सकते हैं कुछ डायपोल्स इस मैग्नेटिक फील्ड के अलोंग अलाइंड हो चुके हैं और यह मटेरियल क्या हो गया? मैग्नेटाइज हो गया। इसी प्रकार से हम देख सकते हैं कि जब हम मैग्नेटिक फील्ड इंटेंसिटी, एक्सटर्नल मैग्नेटिक फील्ड इंटेंसिटी को काफ़ी ज़्यादा बढ़ा देते हैं तो मटेरियल के अंदर मैग्नेटिक फ्लक्स डेंसिटी भी मैक्सिमम हो जाती है। लगभग सारे डायपोल्स अलाइंड हो जाते हैं और फिर इसके बाद यह मटेरियल फर्दर मैग्नेटाइज नहीं होगा। इस वजह से आप देख सकते हैं यह कर्व धीरे धीरे जाके यहाँ पर फ्लैट हो जाता है। इसके बाद हम कितनी भी मैग्नेटिक फील्ड इंटेंसिटी को बढ़ाते जाएं एक्सटर्नली, मटेरियल के अंदर मैग्नेटिक फ्लक्स डेंसिटी कांस्टेंट हो जाएगी और इस कंडीशन को कहते हैं कंडीशन ऑफ सैचुरेशन। यहाँ पर मटेरियल में सैचुरेशन आ गया, इससे ज़्यादा यह मैग्नेटाइज नहीं हो सकता। इसी प्रकार अब हम एक्सटर्नल फ्लक्स को कम करेंगे तो वापस से ये जो डायपोल्स हैं इधर उधर अलाइंड होंगे और अगर हम एक्सटर्नल मैग्नेटिक फील्ड को कम कर कर जीरो कर दें तब हम देखेंगे कि यहाँ पर मटेरियल में थोड़ा सा मैग्नेटिज्म रह जाता है। मटेरियल के अंदर थोड़ी सी फ्लक्स डेंसिटी रहती है, थोड़ा सा मैग्नेटिज्म रह जाता है। इसे बोलते हैं रेसिडुअल मैग्नेटिज्म, जो कि यहाँ पर रिप्रेजेंट हो रहा है बी आर से। यह इसलिए है क्योंकि सारे डायपोल्स वापस से अपनी इनिशियल पोजिशन में अलाइन नहीं हो पाए हैं। आप देख सकते हैं यह डायपोल, यह डायपोल, यह डायपोल अभी भी एक ही डायरेक्शन में अलाइंड है। जिस
Okay, as you can see, as he's saying, these are now still remaining. That is why you are saying it's not going back to complete the original position. Some of them, like this one, and this one, are still arranged in the north-south direction. Okay.
की वजह से मटेरियल के अंदर थोड़ा सा मैग्नेटिज्म बढ़ जाता है। अब इन डायपोल्स को वापस से अपनी इनिशियल पोजीशन में लाने के लिए हमें मटेरियल को विपरीत दिशा में मैग्नेटाइज करना होता है। उसके लिए हम एक्सटर्नल मैग्नेटिक फील्ड को रिवर्स डायरेक्शन में अप्लाई करेंगे। यहाँ से लेकर जैसे जैसे हम रिवर्स डायरेक्शन में मैग्नेटिक फील्ड को बढ़ाएंगे, धीरे धीरे ये डायपोल्स वापस से अपनी इनिशियल पोजीशन में आएंगे और इधर आने पर आप देख सकते हैं मटेरियल के अंदर जो फ्लक्स डेंसिटी है वो जीरो हो जाएगी। उसके लिए हमें कितना एक्सटर्नल मैग्नेटिक फील्ड लगानी पड़ेगी, वो लगभग उसकी स्ट्रेंथ होगी इतनी। इसे बोलते हैं कोहेसिव फोर्स। कोहेसिव फोर्स वह फोर्स है, वह मैग्नेटिक फील्ड है जिसे विपरीत दिशा में अप्लाई करना होता है रेसिडुअल मैग्नेटिज्म को खत्म करने के लिए। इसी प्रकार में हम नेगेटिव डायरेक्शन में ये देख सकते हैं, हमने नेगेटिव डायरेक्शन में मैग्नेटिक फील्ड लगाई हुई है और हम और भी ज़्यादा मैग्नेटिक फील्ड को नेगेटिव डायरेक्शन में बढ़ाएंगे तो फिर यह डायपोल्स विपरीत दिशा में अलाइन होना शुरू हो जाएंगे। अब आप देख सकते हैं काफ़ी सारे डायपोल्स नेगेटिव डायरेक्शन में अलाइन हो चुके हैं, लेकिन अभी भी पूरे डायपोल्स अलाइन हुए नहीं है। तो यहाँ से यहाँ तक तो ग्राफ हमें लगभग थोड़ा सा लीनियर मिलेगा। उसके बाद जैसे जैसे सेचुरेशन आना स्टार्ट होगा यह ग्राफ हमारा ऑलमोस्ट कांस्टेंट हो जाएगा। जैसे हमने एक लिमिट से ज़्यादा मैग्नेटिक फील्ड एक्सटर्नल मैग्नेटिक फील्ड को बढ़ाएंगे उसके बाद हमारा मटेरियल फर्दर मैग्नेटाइज नहीं होगा क्योंकि सारे ही डायपोल अलाइन हो चुके होंगे। अगेन दूसरी दिशा में नेगेटिव डायरेक्शन में भी आपका सैचुरेशन आ जाएगा। वही प्रोसेस अगेन रिपीट होगी। हम एक्सटर्नल मैग्नेटिक फील्ड को कम करेंगे तो यह डायपोल्स वापस से इनिशियल पोजीशन में आने की कोशिश करेंगे। यहाँ आप देख सकते हैं हमने एक्सटर्नल मैग्नेटिक फील्ड को वापस से रिड्यूस करा और हमारे मटेरियल के अंदर मैग्नेटिज्म की फ्लक्स डेंसिटी की वैल्यू इतनी होगी। और इस बार भी वही होगा, हम जब एक्सटर्नल मैग्नेटिक फील्ड को पूरी तरीके से हटा देंगे उसके बाद भी हमारे जो डायपोल्स हैं वो कुछ डायपोल्स अलाइंड रह जाएंगे। अगेन मटेरियल के अंदर रेसिडुअल मैग्नेटिज्म बच जाएगा और इस रेसिडुअल मैग्नेटिज्म को खत्म करने के लिए हमें इस बार से विपरीत दिशा में यानी हमें मटेरियल को वापस से एक्सटर्नल मैग्नेटिक फील्ड की हेल्प से हमें मैग्नेटाइज करना होगा।
Okay, I'm just pausing it over here because somebody just now asked me with regards to okay, whether this area and this area are the same. Okay, so let's see now. Okay, you can see that the length of this is greater than the length of this. So that means this area is less as compared to this. Okay, so that is what I was saying. There is a slight difference. It all depends on what is the material you're using and how quickly these magnets are going to get arranged. Okay, so you will not have it exactly, more or less the same as you can see. Okay, so that is what I wanted to show you. Okay, now where is the eraser? Right. So let's continue with the video.
हम देख सकते हैं यहाँ पर हम इतनी पॉजिटिव फील्ड हमें अगेन लगानी पड़ेगी ताकि हमारा मटेरियल के जो डायपोल्स हैं वो पूरी तरीके से इधर उधर अलाइंड हो जाए और हमारे मटेरियल का रेसिडुअल मैग्नेटिज्म खत्म हो जाए। तो इस प्रकार से यह कर्व ऐसे फॉलो होता रहेगा। हम पॉजिटिव डायरेक्शन में फील्ड को लगाएंगे, हमारा मटेरियल मैग्नेटाइज होगा, सैचुरेशन आएगा, फिर एक्सटर्नल फील्ड को हटाने पर मटेरियल के अंदर मैग्नेटिज्म रह जाएगा। उस मैग्नेटिज्म को खत्म करने के लिए हमें विपरीत दिशा में मैग्नेटाइज करना होगा, फिर जाके हमारे मटेरियल के अंदर फ्लक्स डेंसिटी 0 होगी। फिर अगेन हमें नेगेटिव डायरेक्शन में और ज़्यादा हम मैग्नेटाइज करेंगे एक्सटर्नल फील्ड की हेल्प से, तो अगेन सैचुरेशन आएगा और ये कर्व फॉलो होता रहेगा। हमारे मटेरियल हर मटेरियल के लिए हिस्टैरिसीस कर्व डिफाइन होता है। जिन मटेरियल के हिस्टैरिसीस कर्व के अंदर ज़्यादा एरिया होता है उनमें हिस्टैरिसीस लॉस ज़्यादा होता है और एक आइडियल फेरोमैग्नेटिक मटेरियल क्या होगा, उसके अंदर इस कर्व के अंदर का जो एरिया है वो 0 होगा। मतलब यहाँ से यहाँ तक एक स्ट्रेट लाइन होगी। मतलब जैसे जैसे एक्सटर्नल मैग्नेटिक फील्ड को बढ़ाएंगे मटेरियल के अंदर फ्लक्स डेंसिटी लीनियरली बढ़ेगी और फिर एक्सटर्नल मैग्नेटिक फील्ड को 0 करने पे फ्लक्स डेंसिटी भी 0 हो जाएगी। इसका मतलब आइडियल फेरोमैग्नेटिक मटेरियल का जो हिस्टैरिसीस कर्व होगा वो कुछ इस प्रकार होगा, एकदम स्ट्रेट लाइन, और उसके अंदर जो एरिया होगा वो 0 होगा, यानी उसके अंदर कोई हिस्टैरिसीस लॉस नहीं होगा। लेकिन यह पॉसिबल नहीं है।
फ्रिक्शन तो होगा, इस प्रकार बीएच कर्व भी बनेगा। तो यह होता है हिस्टैरिसीस लॉस। तो आशा करते हैं कि अब आप समझ चुके होंगे कि हिस्टैरिसीस लॉस क्या होता है और आपको यह वीडियो पसंद आया होगा। अगर हाँ
Okay, so hopefully with that video, the explanation that I gave is now become clearer. Any queries or doubts, especially with regard to hysteresis loss? If you're asked in the orals, what is hysteresis loss? Then you should be able to draw this particular BH curve as it called or hysteresis curve and explain, okay, that it is this particular energy that is consumed in making all those tiny magnets come back into the zero position. That means there is no more residual magnetism. That is there on both sides of your AC cycle, okay? And because we are using AC and a soft iron core, we are having this. So you can use cold rolled steel or silicon steel as he mentioned in the video. You are not going to eliminate this curve completely, but this curve, as I said, will become more slim in nature, okay? Ideally, as he said in the video, you would like a nice straight line, but we don't have a material yet that is going to be giving you that straight line, okay? In this world, nothing is perfect. Okay, everybody's understood what is hysteresis loss and the other two losses, I squared R stroke copper losses and eddy current loss. Okay, so your 2% of those losses, remember we said that your transformer is a very efficient device up to 98% efficiency, but the 2% goes in these particular losses. Okay, so we had done auto transformers as far as your motor starters are concerned. So we'll go very quickly through this. Auto transformer, if you remember, has only one winding. Okay, only one winding. Okay, and depending on whether you're having tappings, and remember, as I said, in that motor starter, this was 80%, this was 65%, and this was 50%. Generally, it will be these tappings. Okay, and in your auto transformer, it is going to be the step down. So that means your primary is going to have all the total number of windings, and your secondary is going to have for 50% this much, 65% this much, and 80% this much of winding. So it's going to be a step down transform. Okay, so we know that in this auto transformer, we are going to reduce your current to even lesser than your star delta motor start. Also, the voltage is reduced substantially. So that is why you can use these auto transformers for your motor starter. But there is a big advantage apart from a disadvantage in the sense that your particular starter panel becomes big because you're using this auto transformer. The cost also goes up. There is an advantage in the sense your I squared R losses are less. Why are I squared R losses are less? In your normal transformers, you're having primary and you're having a secondary. That means there's copper windings here, there's copper windings here. So your I squared R losses are going to be more because of the number of copper windings. Here it is only one winding. Instead of having two windings, you're having only one winding. So your copper I squared R losses or copper losses are reduced. And therefore your efficiency of your auto transformer is much higher. You can use your auto transformer even for normal purposes. No big deal. But normally we don't. We use the normal primary, secondary type, whether step up, step down. Okay. Right. Okay. So there are some particular questions. Paralleling of transformers, is that possible? Remember, you have by your MSB, I'm only going to draw that section. Okay, on your MSB, low voltage section, you're going to have two MCCBs, right? Two MCCBs. And in that MCCBs, one is going to be on and the other is going to be off. So I'm drawing the section that is going to be off. And here, this switch will be in the down position. Okay, I won't color it fully, but you will understand. Okay, and here this will be showing here off. And the other one will be showing on condition. And the switch here will be in this direction. Okay. And if you have noticed, there will be a bar in between. Let me color it a different color so that you'll be able to see that color. Okay, there will be a bar inside where it is going to be fixed over here. Okay. You might have seen that. And this is going to your two transformers over here, no? Transformer 1 and transformer number 2 for domestic purposes. So 440 volts is being given to either this transformer or this transformer for your domestic purposes. Okay, so either one of these two transformers are in action. So can these transformers be paralleled? When you're talking about paralleling, means both being on together. Okay, this one is on, that one is off. Can both be switched on together? The answer to this question, no, we cannot parallel because we do not know these following conditions. Whether the voltage amplitude is the same, whether the phase is the same, whether polarity is the same. Now remember, when you're talking about polarity, okay, this may be north and south, but in the secondary, it will be the reverse. Okay. So that is what they mean with that type of polarity. And impedance. What is the impedance that is there on your primary side? What is the impedance there that is there on the secondary side? Whether they are the same in percentage, we do not know. We do not know because we don't have anything to monitor it. On your main switchboard, when you're paralleling your generators, you're having all those things that you can see. You can see the frequency, you can see the voltage, all those things you can see. But over and above that, you're having your plan maintenance, your power management system, which are going to be monitoring each and every of those 4 parameters that are required to parallel your 2 generators. Here, nothing. And if you parallel it, then there are good chances of damaging whatever equipment that is there in your secondary. Okay, so normally this changeover of one transformer to the other transformer is done in dry dock when you are totally blacked out. Okay, you can, if the examiner tries to, lagao chavi, as they say, why not switch off both and then put one of the change over the other? This one you can switch off. Okay, sorry, this one you can switch off and then put this one on and keep this one off. Why can't you do that? Now, here's the other reason. See how he'll catch you. If you are at anchorage, a safe anchorage, then after doing all the risk assessment as to what equipments can be thing, because these are going to several important domestic equipment, which could be equipment on the bridge. If you are in a safe anchorage and after doing all the risk assessment, getting the permission not only from the chief engineer but from company also, then you can do that. But certainly not out at sea. It is just like you wanting to test your emergency generator out at sea. It's something similar to that. So please do not parallel it when the ship is out at sea. So here's another trick question that is asked. If the chief engineer orders you to parallel the transformers, then what? Okay, see, these are all the chavi questions that the examiners can ask you. So you will tell the examiner, sir, respectfully, I will tell the chief engineer, it is not possible, not possible, but giving all the requirements and tell him that equipment can get damaged and most probably will get damaged. Do the risk assessment. And if the risk assessment is come with negligible risk, then you can carry it out. But if the risk still remains, then the chief engineer will think twice. And when you are going to do the risk assessment is not just for onboard, it goes to the company. And the final say is the company. Okay? So don't forget about this risk assessment. And that will tell the chief engineer and everybody else whether or not you can carry it out. Okay? So probably in that risk assessment form, it might be saying vessel safely at safe anchorage, vessel at outer sea. If you put at safe anchorage, then your risk assessment, that value of risk will come down drastically. Okay? Okay, so let me zoom out over here. You can take a screenshot of this.
Excuse me, sir.
Yeah.
Yes, sir. Suppose examiner saying, as you said, for paralleling we need same voltage, same phase, same polarity, and same impedance. So after giving this answer, if examiner say to us, suppose if your voltage, phase, and polarity everything is matched, so still we can parallel the transformer or not. So what we have to say?
So how do you know? Is there any device there that is showing you voltage is same, phase is same, polarity is same, impedance is same? Is there anything to give you that indication?
No, sir. I think so. We are getting only the voltages.
Yeah, maximum voltage. You will not know the phase. Okay,
Yes,
you will
sir.
not know the polarity. You will not know what is the impedance. Okay, there is nothing there to think. Whereas for your paralleling of your generators, first and foremost, you can see the frequency. You can see the voltage on the panel. Those are the only thing. But the phase sequence and all that, that is being done by your power management system. That is being monitored by your power management system. If your power management system was not there, then that check synchronizing unit would have not been there. And then you would have no other alternative but to, again, do the same thing like you're going to be doing there. There you are having something to help you. Here you're having nothing to assist you. Okay?
Yes, sir. Got it. So we have to say no. We cannot parallel the transformer.
No, we cannot. And if he says why not? Then give all these reasons. Okay, we'll see. I'll just open out, just take a screenshot of this. And I think Balvi sir had put it, I do not know whether you're on the written group as well, but he had put it in the written group. Had you all seen that? This morning he has put it on the written group. Okay, I'll just
No,
share.
sir, I didn't saw.
Yeah, okay. I will share it on this group. Just give me a moment. Just give me a moment, guys. I'll just share the thing.
Excuse me, sir.
Yeah, 1 minute, 1 minute.
Yeah.
Okay, I have posted it on both the engineers group as well as ETO oral group. Okay, so just have a look at that. Okay, the second one is with regard to things, so that is really not required. But the one with parallel operation of transformers, just look at that particular thing. Okay. Yeah, somebody wanted to ask me something.
Yes, sir.
Yeah, go ahead. Go
Sir,
ahead.
yeah, regarding point number one, can we say the voltage will always remain the same because ultimately it is connected to the same bus bar via the feeder panel, sir?
Yeah, you can say that. But are the others going to be the thing? I mean, you cannot make out that, isn't it? Yeah, the voltage can be the same. Okay. So apart from that, you cannot make out anything else, isn't it?
Got it, sir. Got it.
Sir, I have questions.
Yeah, go ahead.
Sir, this impedance, percentage of impedance is also given from nameplate. No?
Is also what?
Is also given in nameplate, specification plate.
Yeah, but
Transfer.
but then what is impedance? Impedance
I think
means resistor, reluctance, whether it's capacitive or inductive. Okay. So you'll have the impedance of this particular winding. What about the others? Do you know what is there? What is connected to the secondary at that particular moment? That can vary, no?
yes, sir.
Okay. So many things are switched on and switched off from your secondary in your domestic side. Okay, you might have a hot plate. When I say hot plate, that inductive hot plate might be there. Your hot water boiler, okay, in your pantry and all that. That might cut in, might cut off. Okay.
Yes.
So then your impedance is going to change then, no? So barring your voltage, yes, which you can say can be the same, the rest you do not know. And therefore, if you're going to parallel it, then you can land up with damage to your particular items that are connected to your secondary.
So, sir, at this condition, how they are paralleling transformer dry dock?
At the dry dock, you're completely whenever they are going to black out. When you're blacking out, they're going to do some maintenance, no, on your main switchboard and ESB, correct?
Yes, sir.
Okay, that's the time you do it. You change from one transformer to the other. Correct.
Means
when
that
you
is not
are
paralleling, right, sir?
Yeah, but when your ship is dead, you're only getting power from the show with regard to those lights which those guys are going to be putting. Your ship is completely blacked out.
Okay, sir.
Okay, when the ship is completely blacked out, you don't have lights, nothing.
Okay.
Your ship is blacked out. So you can very safely do this, no? Switch off there, put this in the on position and switch this in the off position. Khatam. And you do it both for your main switchboard as well as for your ESB as well. In your emergency switchboard and emergency generator room, you also have these two transformers, correct?
Mm-hmm.
Yeah, so there also don't forget to do this job over there as well. Okay?
Okay, sir. Okay, sir.
Okay, any other queries or doubts with regard to transformers?
So, what are the maintenance associated with the transformer?
Maintenance with regard to transformers, nothing much. Clean the surface of the transformers because dust can collect, and when dust collects, then you know that the heat dissipation will not be good. So keep that nice and clean. Okay, use a soft cloth, damp cloth. Don't use water. Soft damp cloth is more than enough. If you so require, you can use a soapy solution also for that. When they are painting, if they are going to do painting, okay, remove the old paint by scraping. Otherwise, layer upon layer of paint is going to come on that, and then that is also going to add to the heat. The dissipation of heat won't be good. Okay. Apart from that, check any of the connections that are coming. Obviously, you cannot check the live transformer. You'll have to do it for your one that is not in use. Okay. Other than that, there is no other maintenance that you have to do. Okay. Right. So let us now move on to a new topic. My complete cycle of topics is over with this. And now we start a new cycle, and with the topic of sensors. And then we go through all the
Excuse me, sir.
topics. Yeah.
Sir, regarding this transformer, I have one question.
Now I gave you so much of time and now suddenly you woke up, is it?
No, sir, before starting new topic, that's why.
Yeah, so I gave you at least half a minute. Okay, go ahead.
Sir, the question is related to this welding transformer. What kind of transformer we are using in this welding transformer?
You're using a step-down transformer. Why? What's the reason
To-
why we are using a step down?
To avoid this, what we call, to get the shocks,
Huh?
to avoid the shocks, sir.
Really? You remember the formula?
The current will increase and voltage will come.
Ah, correct. Okay. If you're using a lower voltage, your current can be increased, and that is what we are doing. No, we are increasing the welding current in order to get that weld properly. You've seen the fitter, no, turning that this thing. What is he doing? He's shifting that core so as to increase the current. Okay. So we are reducing that voltage from 440 or whatever that voltage is supplied, and is generally 440. You're reducing it to 24 volts. And by reducing it to 24 volts, you're stepping it down, and by stepping down the voltage, you're increasing the current. And therefore, he'll get that entire range of current that is required to do the welding. Okay?
Sir, voltage is only 24, sir, is there?
Yeah, not necessarily 24, might be 30 volts, might be 50 volts also, but it is step down.
Okay, sir, and what is the amount of current, sir? Means value of the current?
Current can vary quite a lot, right up
Okay,
to
sir,
300, 400 amps.
हाँ सर, वो
Whatever.
हम वो घुमाते हैं तो उससे
हाँ.
जितना करंट चाहो उससे.
Correct. Okay.
ठीक है. Okay,
So it
sir.
depends from welding machine to welding machine. ठीक है.
Okay, sir. Okay.
So some will be very small, वो जो portable जो रहता है तो वो कम current देता है, और जो बड़ा वाला जो रहता है in your particular workshop, that will be having more capacity. ठीक है.
Okay, sir. Okay.
Sir, in the related welding transformer, during welding, the current flow to hull or not? The surveyor asked, sir.
The current will generally flow to the hull, but then if you're going to, that is why when normally it does flow to the hull, but if you're going to do it on a tanker, what does the guy do? What does the fitter do?
सर वो अर्थ कर देता है सर उस वायर को.
His wire.
सर जो
Okay.
जो वेल्डिंग वाली होती है.
Normally क्या करता है ये लोग? Okay, if it is a bulk carrier, there are two, no, one red and one black this thing, ne? So on a bulk carrier, suppose this is going to be the, sorry, let me change the color, then others will get confused. Okay, say on a tanker, he wants to weld this pipe with another pipe. उसको weld करना है. ठीक है? He has to do the weld over here. So on a bulk carrier, he will use the red one for his welding. Okay. And then he will take the black one, which is a short one, and connect it to, he'll chip off the paint or something over there, and he'll connect that the short this thing over here on a bulk carrier or a container vessel. But if you're on a tanker, have you noticed what he does? In this thing, the current will flow through the hull, but in a tanker, you're not supposed to have the current flowing through the hull, as per SOLAS. So what does he do? Okay. He is going to bring that particular black cable all the way from the engine room and connect it to this. You notice that? Anybody on tankers? Okay.
Yes, sir.
So he's going to bring that black cable. So he's going to bring both the red cable and the black cable, connecting the black cable to the pipe. And this one is going to come right from the engine room, just like your red one. And in that way, your current is not going to flow through the hull. You are still earthing that pipe. Okay.
Sir, इसमें और एक क्वेश्चन था, what are the precaution while you follow during welding operation?
Arey, that's nothing to do with me, bhai sahab. I do not know what are the things, what are the precautions. There are a lot of precautions that is going to be taken by safety, mostly by Jalan sir. Okay, all those are safety related issues. So I am not taking safety related issues. So please
sir.
check with Jalan sir. Okay.
Okay, sir.
Okay, so new round of topics starting with sensors. What is a sensor? If it is asked to you in the orals, this is the definition that you are going to give. Everything that is highlighted in yellow, made bold and underlined. Okay, a sensor is a device that would convert a physical parameter. What is the physical parameter? Anything to do with pressure, speed, temperature, okay? Any physical parameter like that is converted into an electrical signal, and that electrical signal can be read at a remote position. Okay, so you're converting a physical parameter into an electrical signal. And that is what is a sensor. So please take a screenshot of this. Okay. Further, everybody knows that sensors are called either active sensor or passive sensor. An active sensor is a sensor that can develop its own power and work using that power. It does not require an external source of power such as 24 volts, 30 volts DC, whatever. It does not require that. It will generate its own power and work based on that power it's generated. And that type of a sensor is called an active sensor. And if he's asking you what is, give an example, thermocouple is the best example that you can give. So likewise, instead of an active sensor, you have the other one, and that is called the passive sensor. And a passive sensor requires an external source of power, 24 volts DC, 30 volts DC, whatever. It requires that power in order for that to work, that particular sensor to work. And an example for that is your resistive temperature detector, RTD for short. Okay. The type of sensors that we are going to be discussing in this chapter are 6. Pressure sensors, temperature sensors, flow sensors, level sensors, proximity sensors, and your fire detection sensors like smoke, heat, and flame sensors. Okay, so please take a screenshot of this. Now, among these 6, as we are going from 1 to 6, one by one, we will be covering each of them. Some of them are not practical for use on board ship. Okay, some of the sensors are not practical for use on board ship. Yet, they are going to be asked in the orals to describe them. So as and when we come across those particular sensors, I will be informing you why it is not practical for use on board ship. Okay, so everybody's taking a screenshot of this. Then we can move on to the very first type, the pressure sensors. So before we move on, please take a screenshot of this. So we saw the definition of a sensor. So what is a pressure sensor then? Okay, so once again, it's a device that is going to be generating a signal. What signal? An electrical signal as a function of a physical parameter. And what is that physical parameter? That particular physical parameter is going to be either pressure or also called force. And as I said, where is it going to be available? That particular reading is going to be available at a remote position. It would give us this reading. That physical parameter is going to be changed into an electrical signal that we are going to be reading at a remote position that is going to tell us what that pressure or force is. Okay, and so that is the definition of a pressure sensor. You take the sensor definition and just add the pressure thing in that. The physical parameter you're going to put as pressure over there. Okay. And quite often combined with that particular definition or that question as what is a pressure sensor, they sometimes ask, what is pressure? And most of us will come with the answer, it is force per unit area. Correct or no? We are partially right. But in the examination, we have to give the correct and full answer. So suppose you're going to tell the examiner, if he's asking what is pressure and we say it is force per unit area, if it is 4 marks, he'll give you only 2 marks. Why to lose 2 marks? You want to get all the 4 marks because each and every mark that you take and put in your pocket, you're going closer and closer to obtaining your COC, correct? And that is what you're doing and that is what you want. So if he's going to ask you what is pressure, get this all important thing. Okay, it is that force or pressure that is applied at 90 degrees. If you can't remember the word perpendicular, remember 90 degrees. It is the force or pressure that is applied at 90 degrees to the surface of an object. So this is that object, this is the surface of that object per unit area. Okay, we got the force per unit area correct. All that you have to add in between is that that particular force should be at 90 degrees. It can't be at this angle, it cannot be at this angle. It has to be always at 90 degrees. Okay, and that is the correct definition of pressure. And if you give that definition, if you have 4 marks, you're getting all 4 marks and safely putting it in your pocket. Okay. So what are the units of pressure? As you can see here, right at the bottom of the page, Pascal, that was one of the first guy who Pascal had discovered this, and therefore it was rightly named after him. Then came megapascals, kg per centimeter square, bar. Everybody knows kg per centimeter square and bar more or less equals, not exactly equal. Okay, you can go online and check, but it is more or less thing. And we take that also on board the ship as both are almost equal to each other. So if we say 1 bar, we can safely call it as 1 kg per centimeter square. It's not exactly equal, by the way. Okay, We take note of that. Okay, so 1 bar or 1 kg per centimeter squared, if you want to change it into MPa, then 10 of that is equal to 1 MPa. 10 bar is equal to 1 MPa, or 10 kg per centimeter squared is equal to 1 MPa. And then you have one more, which is PSI, pound per square inch. This is a very, very small amount of pressure. That pressure is normally you will find whenever you're filling your car tires or scooter tires or motorbike tires. Whatever that indication there on the thing is in pound per square inch. It's a low, very low pressure. In your engine room, it is used for opening and closing of valves via a diaphragm. If you put any pressure greater than a certain amount in PSI, suppose you're going, instead of PSI, you're going to give a bar or kg per centimeter square, then you'll blow that diaphragm to bits. Okay? Is that clear? Oops.
Sir, 1 bar equal to how many PSI, sir? 15?
I would not know the exact thing. You will have to check online. Let me see. I'll just check and see.
15, sir, I think.
1 bar is equal to
14.5 PSI.
14.5, no? Oh, I put the thing wrong. Okay, yeah. 14, yeah, 14.5 something. Okay. Right. Now, in the type of pressure sensors, there are 4 types. You can take a screenshot of this. The capacitive type, the electromagnetic type, piezoelectric type, and the strain gauge. Of which the piezoelectric type, remember as I said, some are not practical for on-board use. So the piezoelectrical type is generally not used on board. When we come to that, we'll see the reason why. Capacitive type is used on board, but nowadays they are more or less done away with that. Okay, you will still find it on some old ships. But electromagnetic, the strain gauge type, yes, still used. Okay, so please remember the piezoelectric type of pressure sensor is not used on board. And when we come to that, we will see the reason why. Okay, so let's take the very first one, the capacitive type of pressure sensor. Everybody is very familiar with this particular formula, correct? C is equal to epsilon multiplied by A divided by D. Epsilon is density, or more correctly called as the dielectric strength. Correct? Area is area of the plates of the capacitor. And D is the distance between the plates. Of the capacitor. Okay, so as you can see here, any one of these three parameters changes, your capacitance will either increase or decrease. If distance between the plates increases, your capacitance is going to decrease. If epsilon and A are going to increase, your capacitance is going to increase. Okay. So keeping that in mind, let us see the capacitance type of capacitance type of pressure sensor. Okay, hope everybody's taking a screenshot of this. Okay, you can take a screenshot of this and then we'll take the description and the working. Okay, so right here is a diagram showing you the very basic capacitance type of pressure sensor. Okay, remember we are going to have two plates and a dielectric, and only then will it form a capacitor, isn't it? So here's one plate shown in red. This plate is going to be fixed and it is going to be taken to one part of the connection of your capacitance type of circuit. Here you have the other plate, but this plate is basically forming the flexible diaphragm. So this plate can move, come back into this position or go inwards. It can go inwards, and depending on how much of force or pressure is acted at 90 degrees, this particular plate will be depressed inwards. This is fixed, is not going anywhere. Only this one will be moving around, depending on what is the pressure or force that is being applied at 90 degrees. And from this plate, you're going to have the other connection going to the electrical circuit. This electrical circuit is going to change. Remember, we said C is equal to epsilon, okay, multiplied by A divided by D. Okay. Now, when this type of pressure sensor is manufactured, the area of the plates is going to be constant. Let's take the dielectric over here as air. Once that air is inside, that is not going to change, so your epsilon is constant. What then can change? Remember, I said this is a flexible diaphragm. If it is not having any force or pressure acting on it, this particular diaphragm will be in this position. And therefore, the distance between the plates, the fixed and this flexible plate, is going to be shown as by the green arrow. But if force or pressure is acted, then this diaphragm will be depressed inwards. And thus, this is the, let's say, the deformed position. It's gone in by so much depending on how much the force or pressure is acting on it. And therefore, the distance between this plate and now here, the fixed plate, has decreased as compared to the earlier distance. So, distance has come down. Therefore, your capacitance is going to be increasing. Capacitance has increased depending on how much of pressure that is acted. And this capacitance is going to this electrical circuit that is going to change this capacitance change into a pressure reading. Okay. How much of the pressure, whether it is calibrated in MPa, bar, kg per centimeter square, PSI, whatever. Okay. And this is how your pressure sensor works. Okay, everybody clear? Any queries or doubts? Everybody's taking a screenshot of this?
Sir, we have one capacitance sensor in on OWS, sir.
Okay.
Sir, it works on the same principle, no, sir?
No. What is that sensor, that capacitor sensor doing?
It measure the flow of the oil, sir.
Yeah, I know. It's sensing the flow of oil. Where does pressure come there? Is it giving you a reading of the amount of oil that is there in your OWS? Is it telling you that?
No, sir.
No, nah. So let's clear your doubt then. Okay.
Okay, sir.
So let's hear, this is your OWS tank. It's generally filled with seawater. And then you're going to be pumping your particular bilges or from the bilge tank or whatever, you're going to be pumping it to that and then overboard. Okay. So let's say this is your overboard valve. And this is overboard. Okay. Okay. Generally you're going to be having two sensors. One sensor here, one sensor here. Now, normally you're going to have seawater. If it is seawater and whatever you're going to be pumping overboard, if that is not having any oil, then seawater will be having epsilon equal to, let's say, 10. But now if oil is going to come, okay, there's 10 over here. This one is also sensing 10. Nothing is going to, there are two sensors, and what these sensors are going to do, they are going to operate certain solenoids and accordingly prevent the oil from going overboard. Depending on what is your circuit on board, they'll either stop the pump or it will have that three-way valve, correct?
Yes.
Right. Now suddenly oil has come. Okay, let's make the oil this color. Okay, let's touch that. What has happened? Epsilon from 10 has now become different, maybe 12.
Yes, sir.
Correct or no?
Yes, sir. Yes.
Okay, and as everybody knows, C is equal to epsilon multiplied by A divided by D. None of these are changing. This one has increased, means capacitance has increased, and therefore that is going to activate that particular solenoid.
Okay, sir. Okay.
Okay, is nothing to do with pressure. It is only sensing the density or epsilon that is changing. See water always, that means, okay, fine, it can go, and anything below that setting. Remember, this is going to that setting, no? There is one thing like that where it has a ducken and then you have that setting over there, no?
Yes, yes, sir. Yes, sir.
Okay, that setting is to set this epsilon.
Okay, sir.
Okay, so as long as the setting is below 12, it will allow you to think. The moment it reaches 12, then it's going to activate and your solenoid for that particular sensor is going to activate and do whatever it is supposed to.
Okay, sir.
Okay.
Okay, sir. Okay. Thank you, sir.
You're welcome. Okay. So let's carry on then. And since we did the pressure sensor, the capacitor type of pressure sensor, let's now go to the differential pressure transmitter because it is doing the very same thing. Okay, please take a screenshot of this. Just 1 minute. Let me take this to the top so you get the proper screenshots. Yeah, you can take this screenshot of this.
Sir, I have one question.
Yeah, go ahead.
Sir, this generator low boil low pressure alarms and trips, this capacitive type sensor is used?
No, in your lube oil low pressure, you're going to be having that pressure switch, isn't it?
Yes, sir.
Okay, there is no pressure sensor as such. This is that pressure switch, which is nothing but a dabba. Okay, there is a dabba like that. Usually, I forget the name of that, Danfoss or whatever it might be. Okay, and then you have that oil which is coming over here. And inside, if you open, there is a spring, isn't it? And then you have that adjustment. Okay, inside, if you take out the cover, you'll find that adjustment whereby you can adjust the spring. And then you have your contacts. Normally open, normally closed contact. I forget what is it, whether it's normally open or normally closed. Okay.
But
So
this
if the
this
pressure,
for trip, na sir, this arrangement for trip.
For trip or even for alarm also. Otherwise, how are you going to have the alarm this thing? Both. There is one for trip and one there for your alarm. Check that. Okay, so
Okay, sir.
same thing is going to think if it is going to be of a certain pressure, then one of these contacts, if it is going to be the normal pressure, then those contacts are going to remain as is. If the pressure is less, then that contact will open and it will give you your either if it is for the trip, then it will give you a trip. If it is for your alarm, it will give you alarm. So first, the alarm will come. So that setting will be much earlier than this trip setting. Okay, so it is this type of thing which is acting against the spring. There will be a diaphragm like thing. Basically, it is like this. Okay, so this is the diaphragm which is sitting in over here. And that diaphragm will be moving the spring up and down. And accordingly, that is going to open and close certain contacts. So let's say this is NC and this is NO. Then accordingly, if it is a NC contact, then that contact will open and then give you that alarm or trip accordingly. Okay.
Okay, sir. But where we use this capacitive type sensor? On board.
Capacitive type of pressure sensor, that is why I said it is hardly used. If at all it is going to be used, it is going to give you a pressure reading at a remote position. And sometimes that is going to be done. In fact, nowadays you're not going to be doing that. You're going to be having a pressure transmitter. Okay, rather than a pressure sensor that is going to give you a remote reading. Okay, so in a pressure transmitter, normally a differential pressure is going to be used to give you that particular reading.
Okay, sir.
Okay, so we'll see this differential pressure transmitter in the form of a differential pressure sensor. What you're going to be using here are two capacitors. Two pressure capacitors. And you will find this mostly for your boiler level, your boiler water level, that is, more specifically. Where an electrical signal is going to be given, which is going to be proportional to the two different pressures. So here you're going to be having, let me zoom in so that you can see more clearly. Okay. So here is going to be one capacitor. As you can see, it is colored darker than this side. So this is one capacitor and this is the other capacitor. The darker one on the left hand side, lighter one on the right hand side. Where are the two plates of the capacitor? This is forming the fixed plate of one capacitor on the left hand side, and a flexible diaphragm is there in the middle. That is forming the second plate. And the dielectric is what is shown here in dark gray, which can be whatever. And here in this case, it is showing it is having a certain oil. Okay. So over here, you're having a diaphragm, and then you're going to be having whatever is going to be connected over here. That pressure is going to be acting on that diaphragm. And that pressure is then transmitted through the oil against this diaphragm, where this diaphragm is going to be moving more towards the right hand side. So this can deflect towards this side. When it deflects towards this side, then the distance between the two plates has increased. Okay, if there is no pressure over here, it's as is, then this particular diaphragm is going to remain right in the middle. Similarly, the capacitor on the right hand side is going to be filled with the same oil over here. And again, the flexible diaphragm is going to be common for this particular capacitor as well. So this flexible diaphragm is common for both the capacitor on the left hand side and the capacitor on the right hand side. Okay, and in a similar manner also, if the pressure is going to be more on this side, then it is going to deflect this diaphragm towards the left. And therefore, the distance between the flexible diaphragm and this fixed plate is going to be more. And that's how your particular capacitance is going to change. So there are two capacitors, and therefore the difference between both, that difference is going to be given to the circuit for your pressure transmission. Okay. So let's see this. If you're taking a screenshot of this, let me zoom out again and clear up this also. Okay, if everybody's taken a screenshot of this, then we'll move down. Okay, you can take a screenshot of this because we are using the same formula, excepting that there will be capacitor number 1, capacitor number 2. The difference between capacitor 1 and 2, that will be giving you the reading. That is why it's called a differential pressure transmitter. Okay, let's understand that a little more now when we'll see the correct type of diagram. Okay, so you can take a screenshot of this. Take it with the notes also. So now you can see it more clearly. So generally one side will be high pressure side, the other side will be low pressure side. Don't confuse that high pressure can't be lower than your low pressure. This is only in significance because if you're going to be using this for your boiler water, remember your drum. Okay, if this is the drum of your boiler, okay, you will be having your low pressure switch or the connection coming from your low pressure over here, and that of your high pressure will be coming from here. So your high pressure thing line will be connected in this manner, and your low pressure thing will be connected in this manner. Why? Here is steam and here is water. Here you have water acting plus the steam pressure acting. So there is two pressures that are there, the steam pressure and the water pressure. This will be your low pressure, So only the steam is acting over here. And therefore, it is relative to everything over here. And that is why it is low pressure. It's called only because only the steam pressure is acting on this. Whereas over here, you're having your steam and your water pressure acting on this diaphragm. So pressure of steam plus the pressure of water acting on this thing, and that is why it is called as the high pressure. Okay. But sometimes you can have your high pressure even less than your low pressure. In other words, if the water level is going to come right down, then your steam pressure will become more than your high pressure, isn't it? Right or wrong? So don't get confused with what is low pressure, what is high pressure. It depends on which one it is connected. So when it's going to be connected to this part, you're getting the pressure of the water plus the pressure of the steam, and therefore it is relatively high pressure. Here it is only the steam pressure, and that's why it is connected to this one, and it is termed as low pressure. And here once again you're having your capacitance 1 and capacitor number 2. This being your flexible diaphragm, then you're getting the output of 1 over here and you're getting the output of 2. The difference is then given as the signal to the output. Give me a moment, guys. Okay. So now let's see what this differential pressure transmitter will be giving. Let me zoom in more so you can take a better screenshot of this. Yes, you can take a screenshot now. Right, so from this diagram, we can see that you can have both the pressures equal to each other. The high side and the low side both can be equal. In which case, this diaphragm in the middle is going to be right in the center. It's not going to move on either side. And the output, the differential output is fed to a differential amplifier, and that is going to give you a 0 voltage output. And that 0 voltage output will be with a particular level within the boiler tank, isn't it? Your drum. Likewise, you can have the higher side having more pressure than your lower side. In which case, the diaphragm is going to be deflected, as you can see here, from the original position. Whatever the distance which is over here has now increased. And therefore, the capacitance over here, okay, would have decreased. When the distance between both the plates has increased, the capacitance would have decreased, isn't it? And here you can see that the capacitance between both these here, this was the distance earlier. Now the distance has decreased, in which case the capacitance on your right hand side would have increased. So the difference between the C1 and C2 is once again fed to your particular differential amplifier, and that will give you a positive output voltage, which is going to tell you when your high is more, that means your water is more and your steam pressure is also there. So that means your level is quite high. The level of the water in your particular drum is quite high. On the contrary, you can have this situation where the low is more than your high. And the reverse of this is going to happen, whereby the capacitance here is increased and the capacitance here has decreased because of the distance between the flexible plate and the fixed plate. And when you're going to have low more than high, that means you're going to get a negative voltage output, which means that your water level has fallen as compared to this one. And here your water level is sufficient. Okay. So everybody's understood the differential pressure transmitter. Any queries or doubts?
Sir, but we have a zero and span adjustment, na? So zero is low and span is high, na, sir?
No, no, no. Your zero and span is to adjust that particular signal. This signal output.
Okay, sir. Okay.
Okay, nothing to do with this. Okay.
Okay, sir.
Okay, so let's now continue. We finish with the pressure type. And now let's go to the strain gauge. Okay, the strain gauge type of pressure sensor. Okay, please take a screenshot of this and then we will discuss. Okay, everybody taking a screenshot and then take a screenshot of this diagram. Okay, so this type of strain gauge or pressure sensor, he will ask you to explain. And if he is asked what type of, or rather give an example where it can be used, then this is the example that you can be given. Okay, that it is used for your hull stress monitoring system. I have not been on a bulk carrier for a very, very long time. And that too, a Cape size bulk carrier, because the small size bulk carriers don't have this hull stress monitoring. Cape size bulkers, when I was on a bulk carrier long, long ago in the early 90s, I was working for a company called P&O. You would only associate P&O with ferries and passenger vessels, but they also at that time had bulk carriers. Okay, and on those ships, they were greater than 100,000 ton dead weight. And on their deck, so this is a bird eye view of the deck looking from the top. On the main deck, on the port side, starboard side, and one right by the forecastle, you had rectangular boxes like this. And within those rectangular boxes, you had a solid stainless steel rod, solid stainless steel rod, one side of which was welded to the deck. The other side too was welded to the deck, and the other side had all the electronics, and that electronics terminated in what we very well know is a Wheatstone bridge. Now, these boxes were arranged in such a way that if you had these on your port side, then in between two on the port side, you had one on the starboard side. Like you can see here, two on the port side, in between those two, you had a thing. So the number on one side would be more than the number on the other side. Now, what is the stainless steel rod going to do? You know that stainless steel is a very, very strong metal. But surprisingly, this rod, stainless steel rod, is going to be bending in sympathy with that of your vessel. Your vessel can hog, in which case your accommodation side and your bow side goes down, your midship comes up, isn't it? That is called as hogging. And the reverse is going to happen when your accommodation and bow comes up and your middle of the ship is going to sag, and that is what is called as sagging. So your ship hogs and sags in very rough weather, which means a lot of stress and strain is coming on your ship's hull. It can break in two at any given moment, especially if you are carrying iron ore. Your ship's hull becomes like a dry twig. Bend it too much, whether hogging or sagging, and it's going to snap in two and sink. Okay, just to give you what happened some time ago when in the early 90s, this was not early 90s, it was about late 90s, around 97, 98, I'm not sure which year it was. There was a ship called Mineral Diamond. The Mineral Diamond was belonging to a company called Bocimar. Bocimar. I'm not sure whether that company is there or not. It was a Belgian company that had only Capesize bulk carriers, all greater than 125,000 deadweight. And this particular Mineral Diamond in particular, I think was about 150,000 deadweight. She had come to the port of Dampier in Australia, which, as you know, is at the northwestern tip of Australia. And the port of Dampier is famous for exporting iron ore. So she had loaded iron ore and sailed out. Hardly 2 days away, she ran into a very severe cyclone in the Indian Ocean. Very severe. Next thing we know that ship has disappeared. How they came to know that the ship has disappeared is because the EPIRB was released and was sending out a distress signal. That ship had broken into and sank in less than 5 minutes with the loss of everybody on board. What would have happened is possibly, and they didn't have this system on board. Okay, it was long ago. They didn't have this system on board, this hull stress monitor. So possibly when the chief officer had loaded, he had probably loaded the ship incorrectly, where the ship was stressed too much. And therefore, when they ran into that severe cyclone, that stress had caused either to hog or sag excessively and for the ship to break in two. And that's why it sank. All hands lost. Okay, had they had this hull stress monitoring system on board, possibly they may have saved the ship. because it is giving you that particular stress of the hull even whilst loading or even whilst discharging. Okay, normally you also load iron ore in Brazil. There is one particular port, I forget the name of that port, where they, with lightning speed, they load your ship. And our ship had this our particular fleet of bulk carriers and P&O had this hull stress monitoring system, and therefore there was no incident. The moment that hull stress monitoring system gave an alarm, they would stop the loading. Chief officer would stop the loading and tell them to shift to another thing, another hatch. But an instance had happened whereby they were loading another ship and we were at anchorage at that time waiting our turn to berth. They were trying to throw that ship out as fast as possible, loaded that ship, and instead of throwing that ship out as soon as possible, it landed up, they broke the ship in half, and that ship sank at the berth with all its cargo. So instead of doing it within 48 hours, it landed up for some months that particular port was closed. And we had to go to another port to load our cargo. Okay. So tomorrow I am going to take class. I will tell the institute to give me a class tomorrow. So we will discuss this type of strain gauge pressure sensor tomorrow, and we will also see a video. Okay. So I'll call a halt to today's class. Any queries or doubts up to this particular point? Okay then, guys. So thank you very much for joining, and I'll see you again tomorrow at 11 o'clock.
Thank you.
You're welcome.
Thank you.
Welcome.